Thanks, Rose, and good afternoon, colleagues. So in my 15 minutes, I want to talk about some of the subtleties around human-oriented notions such as unexpectedness and surprisingness. I'll try and illustrate why these are concepts that are worthy of computational thinking as well as human thinking, and try and hint at some of the underlying technical challenges. Broadly speaking, I'm talking about topics in artificial intelligence and a field that itself is considered to have been founded in around 1956. I'm not sure what Trevor Pearcey thought of the field at the time and as it matured. Even in the 1940s, he wrote on how computation could be harnessed for many uses beyond what was viable in his own era, and Paul's highlighted that for us. So I figure there's bound to be a connection, as I hope there is, what I'm going to talk about that he would appreciate. But first, in keeping with the theme of the symposium, I wanted to start with a little history. Let me go back 55 years, and here's an image reminiscent of CSIRAC Mark I, of the room-filling machinery. The man in the photo is Sergey Brin's father, Sergey Brin being the American computer scientist who, together with Larry Page, co-founded Google. And the caption, which is not shown here, reads as follows: "Scientists from the Rand Corporation have created this model to illustrate how a home computer could look in the year 2004. However, the needed technology will not be economically feasible for the average home. Also, the scientists admit that the computer will require not yet invented technology to actually work, but 50 years from now, scientific progress is expected to solve these problems. With teletype interface and Fortran language, the computer will be easy to use." Of course, this prediction was far too conservative about what would be accomplished. Indeed, some have quipped that we are fortunate the mouse eventually overtook the steering wheel as the primary accessory. But there's some very sharp observers among you who might be puzzling over the vintage of some of the electronics on display. Indeed, consider this photo, which is of a physical display at the Smithsonian in Washington. But the display is not labelled as a life-size replica of a 1954 prediction of a home computer. It's labelled as a full-scale mock-up of the control room of a nuclear-powered submarine. So, if you can read the text at the bottom, you'll be able to confirm that no home computer model, as in the top image, was ever created, nor was it published in any 1954 edition of Popular Mechanics. You can actually find those on the archive and check them if you wish. The image is a manipulation of a real photograph that was entered in a Photoshop contest. It's an example of what's known sometimes as photography. And indeed, if you search the internet, you'll find some accounts that still believe this is an authentic photo, and others that tell the story of the hoax. But if we think about it, even if this was a real situation, that somebody might predict in 1954 falsely what things might look like in 2004, it's a shrug. It's a prediction, but it's not surprising, not unexpected. To create a strong prediction, one that, if it fails to eventuate, triggers surprise for the hearer, relies on the audience either having blind faith in the predictor or the prediction being supportable by some form of accessible evidence. A first cut definition of surprise would typically be something like astonishment through unexpectedness or expectation failure. So surprise draws on two elements. One being able to characterise what unexpectedness means, and then what types of unexpectedness actually create human responses in the form of astonishment or wonderment. And then there are further forms of surprise. There's mismatch-based surprise, where the agent has an anticipatory kind of active representation of the next input, but when there's a gap between, or an inconsistency between that expectation and what actually arrives as the next input, that's a clash. For example, I have an appointment with Joan at a certain time. I know Joan is reliable, but Bill arrives without notice instead. That's mismatch-based surprise. Contrast this with a form of surprise that arises when the input data doesn't conflict with an active expectation, but just with some background or passive expectation. For example, I'm waiting at my usual tram stop, and across the road I see Arthur, my friend, but he lives in another state, and I wasn't aware it was in town. I'm surprised, but not because of any active expectation that's been conflicted. It's just an inconsistency with some sort of background context. And there are other variations, of course. To pursue this a bit further, though, I'd like to turn to a domain where surprise is deliberately constructed by a conjurer or a magician, who create conflict very deliberately by taking advantage of characteristics of the human observer's memory and other aspects of perceptive apparatus. And perhaps unsurprisingly, there isn't an agreed theory of surprise in psychology, but there often definitions are grouped into two camps. There's the probability grouping and the sense-making camp. In the sense-making approach, one definition argues that people's perception of surprise is related to their estimate of the cognitive work involved in explaining the event. That is, surprises are more surprising when they're harder to explain. In the probabilistic view, one definition talks about the distance between Bayesian prior and posterior belief distributions. Such approaches, of course, rely on assumptions that probabilities can meaningfully be assigned to the situations and that human responses can be adequately captured by probabilistic rules. For those in the know, that's a point that comes with a variety of ready critiques and an even wider variety of counter-propositions. But related to this, together with colleagues, I'm working on a project that is drawing on principles that are elucidated in the context of conjuring, but looking to apply these in other domains to computationally generate surprising and deceptive behaviours. And our starting point is to observe that a sizable subcategory of conjuring tricks have a particular general structure. There are two parallel event sequences. There's the effect event sequence that the spectator, the audience, believes is happening, and then there's the method event sequence, which is the actual events that the conjurer is conducting. The conjurer has the task of maintaining naturalness, of ensuring that the spectator is focusing elsewhere at selected moments when sleight of hand is happening over here, and so on, in order to build up a trajectory of events, a sequence of things that are happening that the audience can have confidence are just leading naturally from one to another, to another, to another, and then, at the moment of reveal, something has happened that is surprising. But what's being shown is not, in fact, what the method sequence, not what indeed was happening. That is all to be invisible. And the conjurer is relying on limitations with the human audience's memory, perception, etc. There's some wonderful books about some of that. So in broad outline, what I've tried to say is that if you think about it, this is, say, a 1, 2, 3, 4, 5, 6 phase trick of some kind. The white circles indicate the phases as seen by the observer, the effect sequence. The grey ones signify the actual activities of the conjurer, the method sequence, and the reveal is happening here, and the gap is the gap in reality between what the spectator is seeing and what is really the case. And over here what you have is that the believed and anticipated state, which follows very naturally from all that the observer has been paying attention to, actually conflicts with the state that is available at the end that has been constructed by the conjurer. So that's a kind of schematic of a very core idea. And returning to the theme of the talk, which is computing the unexpected, what computational apparatus might be needed in order to be able for synthetic computer-based reasoning mechanisms to mimic such reasoning and such inference? And bear in mind also that the magician, while performing the effect actions, has to be thinking about and understanding what the spectator is believing as various events unfold. So think of the pea and thimble trick. The spectator knows the pea is under a certain thimble because the pea was seen being handled, put on the table, the thimble was put on top. The spectator knows the table and the thimble don't have holes, they've been inspected, that they obey the usual laws of physics, etc. The spectator is also hypervigilant and thinking, oh, I know I'm going to be tricked, I just don't know when, I'm going to be very watchful of that. So the conjurer has to factor all that into account. These are forms of what are called theory of mind reasoning. Not only does the system have to be able to manipulate facts, but beliefs about facts, and think of this as second order, one's beliefs about the other's beliefs. And indeed, for more complex tricks, the magician's beliefs about the spectator's beliefs about the magician's beliefs, etc. So from a computational perspective, one can represent these things symbolically. It relatively quickly turns into a kind of combinatorial explosion that gets challenging computationally. In fact, that's a nice link to the next talk. But at this moment, you'll be thinking, well, I'm most of the way through the talk and I've said nothing about computation and applications. So let me switch to a couple of quick applications and then wrap up. So consider the business of data mining. Right? You're a retail analyst and you have access to a mountain of data. One of the reference papers here, an example which has a few 100 million receipts from a few thousand retail stores gathered over a year in some country. And the analyst is interested in uncovering buying patterns, associations between user segments and product categories. Young people in the north consume beer, or people who purchase sausages and mustard also buy Riesling. Algorithms for generating such association rules, there are many. And there are also many rules to be found. Tens of thousands of associations of quite a high degree of confidence can be found in the mentioned data set. But if you're the analyst, you don't want a list of 10,000 associations that come up. You want the interesting ones, you want the unlikely ones, the ones that don't already match what you know. To be able to extract something useful from the data is a more challenging task. And what this table that you deliberately can't read is in this, there's a field called interestingness measures. There are 30 plus interestingness measures, all have their own technical characteristics. Here are sort of probabilistically flavoured about half of those 34 interestingness measures tested against the data set in order to be able to evaluate the quality of different approaches to definitions of interestingness for this task of filtering out interesting rules that are going to be useful for the analyst. Details are not important. The point here being that there's a serious problem of trying to understand what's a notion of interesting that can be applied to this kind of task in data mining. And now to my final, my next domain, final domain, serious games. Consider the problem of designing software that controls characters in some kind of simulation environment. Might be a simulation for entertainment, might be for training. It might be connected to a joystick that's being used for rehabilitation. You're trying to encourage the user in some physical way to not just go through the same pattern, but make some novel moves. And so you have to be able to understand what novel means in a given context, novel or unexpected or surprising. If it's an educational context and everything's very repetitive, quickly lose interest, lose engagement, not effective. So again, this same challenge of being able to define and computationally generate surprising, interesting behaviours. And it turns out, if I'm going to isolate a point where the challenge of generating such interesting behaviours has much in common with the conjuring task. Because what do you need to be able to do? The system needs to be able to represent what the human user observes and believes. So a system designer must deal computationally with this symbolic theory of mind. I believe you believe, maybe I believe you believe I believe, and so on. And that's this cartoon here is trying to give you a visual of that nested belief reasoning that must sit inside computationally in some form or other, systems that have the capability to identify and generate novel, interesting, surprising, unexpected, choose your term. Of course, the system also has to do a bunch of other things, has to represent and track user inferences, allow for multiple alternate paths, and all done in a way that can be, the present can be rolled forward to model and produce projections and expectations, and eventually to look back to generate explanations, which is a whole other and very popular branch of contemporary artificial intelligence. In conclusion, I hope that Trevor Pearcey would see all of this as an interesting, perhaps somewhat unexpected, if not surprising, set of developments that derived from the foundational work that he led 70 years ago. I also hope I've left you with a little appreciation of the positive benefits and challenges of designing computation for the unexpected. Thank you.